NENOMATICA, where mathematics meets YouTube excellence. Welcome! Today we'll learn how to identify like terms in algebraic expressions. Let's start with what like terms actually are. Like terms share exactly the same variables raised to the same powers. Only their coefficients differ. Let's look at some examples of like terms. The square root of 3 times x squared y, negative 3 times x squared y, and 7 times x squared y are all like terms. Notice that all three expressions have the same variable part, x squared times y. These are like terms despite having different coefficients. Now, let's look at terms that are not like terms. Negative 5 times x cubed times y squared and 3 times x squared times y cubed are not like terms. These are not like terms because one has x cubed and y squared, while the other has x squared and y cubed. The variable exponents differ. Let's try a challenge. Which of these expressions are like terms? We have A, 4x squared y, B, x squared y squared, and C, negative 2x squared y. Take a moment to think about it based on what we've learned so far. Let's analyze each expression. For option A, the variable part is x squared y. For option B, the variable part is x squared y squared. For option C, the variable part is also x squared y. Therefore, options A and C are like terms because they have the same variable factors with identical exponents x squared times y. Now that we've explored like terms, let's summarize what we've learned. Like terms have the same variable factors with the same exponents. Only the coefficients can differ. Identifying like terms is essential for simplifying algebraic expressions. For practice, try creating your own sets of like terms and identifying like terms in various algebraic expressions. This skill will be extremely helpful as you progress in algebra. Welcome to today's math lesson on combining like terms in algebra. When working with algebraic expressions, we need to identify when terms can be combined and when they cannot. The basic rule for combining like terms is that terms with identical variable parts can be combined by adding or subtracting their numerical coefficients. If two terms have the exact same variables raised to the exact same powers, then they are like terms. Let's look at the example from our problem. 3x squared y plus 5 times 2y. First, let's identify the separate terms in this expression. Let's analyze the first term. 3x squared y can be broken down into its coefficient and variable parts. The coefficient is 3, and the variable part is x squared times y. Now, let's look at the second term. 5 times 2y. First, let's multiply the numerical values. 5 times 2 equals 10. So this term is 10y. The coefficient is 10, and the variable part is just y. Let's put these terms side by side and compare their variable parts to determine if they are like terms. The first term has x squared y, while the second term has only y. Since the variable parts are different, they are not like terms. For terms to be like terms, they must have exactly the same variables with exactly the same exponents. In our example, the first term has x squared y, while the second term has only y. The first term has an extra factor of x squared compared to the second term. Therefore, these are not like terms and cannot be combined. Let's see an example where terms can be combined. Consider the expression 3x squared y plus 7x squared y. These are like terms because they have identical variable parts x squared y. So we can add their coefficients. 3 plus 7 equals 10. Thus, 3x squared y plus 7x squared y equals 10x squared y. Going back to our original expression, 3x squared y plus 5 times 2y. Or more simply, 3x squared y plus 10y. Since these are not like terms, this is already in the simplest form. We cannot combine them further. Let's summarize what we've learned. Terms can only be combined if they have exactly the same variables with the same exponents. In our expression 3x squared y plus 10y, the variable parts are different, so they cannot be combined. Remember, when checking if terms are like terms, always focus on the variable parts and their exponents. Welcome to our lesson on the distributive property in algebra. Today we'll learn how to understand and apply this fundamental property, which connects addition and multiplication. Let's begin with the formal definition of the distributive property. The distributive property states that for any numbers or algebraic expressions a, b, and c, we have a times the sum of b plus c equals a times b plus a times c. In simpler terms, when we multiply a number by a sum, it's equivalent to multiplying each term individually and then adding the results. Let's examine a specific example. Consider the equation 5ax equals open parenthesis 3 plus 2 close parenthesis ax. Using the distributive property, we can rewrite this as 5ax equals 3ax plus 2ax. Now, let's look at the original example again. From a different perspective, notice that we can undo the distributive property as well. If we start with 5ax, we can express it as 3ax plus 2ax by splitting the coefficient 5 into the sum of 3 plus 2. This is actually the reverse of the distributive property, sometimes called factoring. Now, let's tackle the first practice problem from our exercise. We have 9ma squared x equals open parenthesis 7 plus 2 close parenthesis ma squared x. Using the distributive property, we can rewrite this as 9ma squared x equals 7ma squared x plus 2ma squared x. Let's move to our second problem. We have 4axy squared equals open parenthesis 9 minus 5 close parenthesis axy squared. Using the distributive property, this becomes 4axy squared equals 9axy squared minus 5axy squared. And finally, our third problem. We have 12ab squared x equals open parenthesis 8 plus 3 plus 1 close parenthesis ab squared x. Using the distributive property, this becomes 12ab squared x equals 8ab squared x plus 3ab squared x plus 1ab squared x. Notice the pattern in all these examples. We start with a single term that has a numerical coefficient. Then, we express that coefficient as a sum or difference of numbers. Finally, we distribute the variable part to each number in the sum. In general, if we have a coefficient k, and we can write k as j plus m, then k times x equals j times x plus m times x. Let's visualize this property with a geometric interpretation. If we have a rectangle with width a and length b plus c, its area can be calculated in two ways. One way is to multiply a times the sum of b plus c. Another way is to split the rectangle into two smaller rectangles and add their areas, a times b plus a times c. Both calculations yield the same result, which is a visual proof of the distributive property. The distributive property is essential in algebra for several reasons. First, it allows us to simplify complex expressions. Second, it helps us factor expressions, which is the reverse process of distribution. Third, it connects the operations of addition and multiplication. And finally, it forms the foundation for many algebraic techniques like equation solving. Let's summarize what we've learned today. The distributive property states that a times the sum of b plus c equals a times b plus a times c. We can also use this property in reverse to factor out common terms from an expression. This property is essential for algebraic manipulations and problem solving. Welcome to this lesson on using the distributive property. Today we'll learn how to simplify algebraic expressions by factoring out common terms. The distributive property is a fundamental concept in algebra that allows us to simplify expressions with common factors. Let's start with our first example, 5x plus 2x. We can see that both terms have x as a common factor. By factoring out x, we get x times the sum of the coefficients, 5 plus 2, which equals 7x. Moving on to our second example, 9 ab minus 3ba. First, note that ab equals ba due to the commutative property of multiplication. So we can rewrite this as 9 ab minus 3 ab. Now we can see that ab is a common factor. Factoring out ab, we get ab times the difference of the coefficients, 9 minus 3, which equals 6 ab. Let's look at our third example, 3xy squared minus 4xy squared. Here, xy squared is our common factor. Factoring it out, we get xy squared times the difference of the coefficients, 3 minus 4, which equals negative 1. So our result is negative xy squared. Our fourth example is more challenging. 1/5 y squared minus 2/7 y squared. Here, y squared is our common factor. Factoring it out, we get y squared times the difference, 1/5 minus 2/7. To subtract these fractions, we need a common denominator. The least common multiple of 5 and 7 is 35. So 1/5 equals 7/35, and 2/7 equals 10/35. 7/35 minus 10/35 equals negative 3/35. So our final answer is negative 3/35 y squared. For our final example, let's look at for xyz plus 2 yzx minus yzx. Using the commutative property, we can rewrite yzx as xyz. So our expression becomes 4xyz plus 2xyz minus xyz. Now we can see that xyz is our common factor. Factoring it out, we get xyz times the sum of the coefficients for plus 2 minus 1, which equals 5xyz. Welcome to our algebra lesson on simplifying algebraic expressions. In this video, we'll learn how to simplify different types of expressions by combining like terms and factoring out common factors. Let's start with our first example. We need to simplify 4x squared minus 2x squared. This expression has two terms with the same variable part, x squared. When we have terms with the same variable power, we can combine them by adding or subtracting their coefficients. So we can rewrite this as open parenthesis 4 minus 2 close parenthesis multiplied by x squared, which equals 2x squared. And that's our simplified expression. Let's move on to the next example. For our second example, we need to simplify 0.5t minus 3.5t. Again, we have terms with the same variable, t. Let's combine the coefficients. Factoring out t, we get the expression open parenthesis 0.5 minus 3.5 close parenthesis multiplied by t. Calculating 0.5 minus 3.5 gives us negative 3t. So our simplified expression is negative 3t. For our third example, let's simplify 7ab plus 3ab. Here we have two terms with the same variable part, ab. We can combine them by adding their coefficients. Factoring out ab, we get open parenthesis 7 plus 3, close parenthesis ab. 7 plus 3 equals 10. So our simplified expression is 10ab. Let's look at our fourth example, 12ab squared minus 5ab squared. Just like before, we have terms with the same variable part, ab squared. We can combine them by subtracting the coefficients. We can rewrite this as open parenthesis 12 minus 5 close parenthesis ab squared. 12 minus 5 equals 7. So our simplified expression is 7ab squared. For our fifth example, let's simplify 2xy squared minus xy squared plus 5y squared x. First, notice that all terms contain xy squared. In the last term, y squared x can be rewritten as xy squared since multiplication is commutative. Rewriting, we get 2x y squared minus xy squared plus 5xy squared. Factoring out xy squared, we get open parenthesis 2 minus 1 plus 5 close parenthesis x y squared. Adding these coefficients, we get 2 minus 1 plus 5 equals 6. So our simplified expression is 6xy squared. For our next example, we'll simplify 3a squared b cubed plus 5a squared b cubed minus 7a squared b cubed. All terms contain the same variable part, a squared b cubed, so we can factor it out and combine the coefficients. Factoring out a squared b cubed, we get open parenthesis 3 plus 5 minus 7 close parenthesis a squared b cubed. Adding these coefficients, we get 3 plus 5 minus 7 equals 1. So our simplified expression is a squared b cubed. Let's move on to a slightly more complex example, ab over 2 minus ba over 3. First, note that ab and ba represent the same expression because multiplication is commutative. So we can rewrite this as ab over 2 minus ab over 3. Factoring out ab, we get ab open parenthesis 1 over 2 minus 1 over 3 close parenthesis. To subtract these fractions, we need a common denominator. The least common denominator of 2 and 3 is 6. Converting to equivalent fractions with denominator 6, we get ab open parenthesis 3 over 6 minus 2 over 6 close parenthesis. Subtracting, we get ab times 1 over 6, which equals ab over 6. For our final example, let's simplify a more complex expression with fractions. ab over 2 minus 2, ab over 3 plus ab over 4 plus 5, ab over 12. All terms contain ab, so we can factor it out. Factoring out ab, we get ab times open parenthesis 1 over 2 minus 2 over 3 plus 1 over 4 plus 5 over 12 close parenthesis. To add and subtract these fractions, we need a common denominator. The least common denominator of 2, 3, 4, and 12 is 12. Converting to equivalent fractions with denominator 12, we get AB times open parenthesis 6 over 12 minus 8 over 12 plus 3 over 12 plus 5 over 12 close parenthesis. Adding and subtracting these fractions, 6 minus 8 plus 3 plus 5 equals 6 over 12. Simplifying 6 over 12, we get 1 over 2. Therefore, our final answer is AB over 2, where we'll work through algebraic equations and solve for the missing values. We'll go step by step through each equation, applying algebraic operations carefully to find our answers. Let's begin with our first example. We need to find the missing term in the equation 9a squared equals 4a squared plus blank. We'll solve this step by step. First, we need to isolate the variable terms on one side of the equation. Let's start by subtracting 4a squared from both sides. Next, we can simplify the left side by combining like terms. 9a squared minus 4a squared equals 5a squared. So, we found that the missing value is 5a squared. Let's move on to our second example. We need to find the missing term in the equation 12ax equals 16ax plus blank. First, let's subtract 16ax from both sides to isolate terms with the variable on one side of the equation. Next, we can factor out the common term ax. So, we found that the missing value is negative 4ax. Let's continue with our third example. We need to find the missing term in the equation 2ax plus blank equals ax. To find the missing term, we'll subtract 2ax from both sides. Now, we can factor out ax from the right side. So, we've found that the missing value is negative ax. Let's solve our final example. We need to find the missing term in the equation ab over 2 plus blank equals 3ab over 2. To isolate the missing term, we'll subtract ab over 2 from both sides. Now, we can combine the fractions on the right side because they have the same denominator. Therefore, the missing term in our last example is ab. Great job! We've successfully solved for all 4 missing terms in our algebraic equations. Let's summarize our findings. In the first example, the missing term was 5a squared. In the second example, the missing term was up. We've successfully solved for all 4 missing terms in our algebraic equations. Let's summarize our Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.